All right, so I hope everyone is here that is intending to be here. Let me start just by reminding you what I talked about last time. So remember, we're talking about manifolds with non-negative Ricci curvature. So I take a manifold M, dimension n, metric G, and the Ricci curvature greater than or equal to 0. And really the situation we're interested in is complete non-compact. Okay, so last time I went through the Laplacian comparison theorem, which says that in a suitable sense, the Laplacian of the square of the distance function from some point is less than or equal to what it would be in Euclidean space, which is just 2n. So here rho is, so if you like, rho of x would be the distance of x from some point x naught. And then from that we got the volume comparison result, which allows us to compare the volumes of metric balls of comparable radius. So that says that the volume of, let's say, the ball of radius big R, about x naught, is no bigger than big R over little r to the power n times the volume of the ball of radius little r, about the same center. Okay, for little r less than big R. And then the last thing I did last time was this Poincare inequality on metric balls, which says that if I integrate on, let's say, the ball of radius r about x naught, gradient phi squared, then that dominates with some constant, which is depending on n divided by r squared times the integral of phi squared. This is for any, so there's a Dirichlet Poincare inequality. So this is really any phi which is 0 on the boundary. And I guess otherwise just W12 is enough for this. So it'll be W012 function. Okay, so that's where we got to last time. Are there any questions anyone would like to ask about any of the stuff I covered? No? Okay. Right, so what I wanted to start with today is proving Yau's gradient estimate for harmonic functions. So this, well, let me tell you what it says. It's a beautiful application of the maximum principle to prove a gradient estimate. So that really it says that if I have a positive harmonic function, so u greater than 0 and Laplacian equals 0 on ball of radius r about x naught in M, and of course I'll just assume throughout that we have Ricci non-negative and so on, then okay, we get an estimate on the gradient of the log of u at any point. So let me write it this way. If I look at the gradient of the log of u at a point x, and I multiply by r squared minus rho of x squared, and again, rho is going to be the distance from x naught, then this is bounded by, well, some dimension-dependent constant. And again, to get the scaling right here, I need a r. Okay. So that would be, that holds everywhere on this ball. Okay. So, yeah, it's a very nice estimate. It gives you, in particular, a bound on the gradient of the log at the center point, and the estimate just degenerates at the boundary in this particular way, like r squared minus rho squared. This, perhaps to motivate this, it's interesting to look at the two-dimensional case. I won't really spend much time doing that, but in the two-dimensional case, so think of the case of the ball of radius 1, so little r equals 1, then this 1 minus distance squared at the front would turn the metric on the unit ball into the hyperbolic metric on the Poincare disk. So this is really saying that if I look at this harmonic function as a harmonic function on hyperbolic space, then it has bounded gradient. So that's maybe one way to motivate this statement. Okay, so let me prove that. As I said, it's just an application of the maximum principle. Let me simplify matters by just assuming that we have, without loss of generality, r is 1, which you can do just by scaling the metric. If I multiply the metric by a constant, then I don't ruin the fact that the Ricci curvature is non-negative or completeness or anything like that. So then we're given our function u, which is harmonic and positive, and let me write v to be the log of u. Okay, so this is well defined, and just a simple computation tells me that the Laplacian of v, okay, so this would be, sorry. Yeah, okay, so let me do the computation. So it's di of diu over u, and so that would be Laplacian u over u minus gradient u over u squared. Okay, and of course the Laplacian is 0, so this is just minus gradient v squared. So that's the equation satisfied by v. Now, I want to prove this gradient estimate. So what I'm going to look at is really let's look at the gradient squared of v. So I'm going to let f be gradient v squared. And then I just want to, if I just differentiate this equation for v here, equation 1.
Hey Ben, on the left of equation 1, I don't think you want 0 equals Laplace v, right?
No, you're right. Thanks. Yeah.
All good.
It's just computing Laplace v. Thanks. Yeah. Okay. So if I just differentiate this equation 1, then okay. So I'll get. Okay. So let me write that as okay. Gradient I, and now I'll write this as Laplacian v plus gradient v squared, and gradient v squared is just f, right? So in the first term, I can commute the gradient past the Laplacian, so that would be give me gradient Laplacian of gradient v at the expense of a curvature term, which is Ricci curvature. So I get Ricci IP gradient pu, and then I get just a gradient f. And so now to get the Laplacian of v, I just multiply that by twice gradient v, right? And so you'll get Laplacian f, and then I'll get the cross terms in the Laplacian, which is minus 2 Hessian squared of f. I'll get a minus 2 Ricci gradient v, and this last term just becomes a plus 2 gradient v dot gradient f. Okay. Now, so I'm just going to, I won't try and get the best constants here, so I'm just going to estimate this. Okay, so I get Laplacian f. The Hessian squared is at least as big as 2 over n times its trace. So that'll be Laplacian v squared. The Ricci curvature I'll throw away since it's non-negative. And then this last term would be bounded by, okay, so gradient v is no bigger than square root of f. So I'm going to write that as square root of f times the length of gradient f. Okay, and then finally the the equation 1 again says that Laplacian v is just minus f, right? So this is just gradient f. I get a minus 2 over n f squared, and this last term 2 root f, gradient f. Okay, so that's next equation. I'm going to call that equation 2 because I'll use that again in a minute. Okay, so now to get this estimate, we have to multiply by this r squared minus rho squared. In this case, just 1 minus rho squared. So let me just write phi is 1 minus rho squared. Okay, where rho is this rho is the distance from x naught. Okay, so what I need to, okay, so the function, okay, so we're really interested in phi squared times f. That's the quantity which we claim is bounded here, right? So I'm going to call that g. Okay, so this is really the function that I'm going to apply the maximum principle to. So let g be phi squared f. Now the nice thing about this is that on the boundary of the radius of the ball, so in other words, in this case r is 1, right? So on the boundary of the ball, we have g is 0. So that means we know that g attains an interior maximum somewhere, unless it vanishes, of course, which is a trivial case. So let's say this happens at some point x bar in B1. Okay, and then the rest of the computation is just looking at what happens at x bar. Since it's a maximum point, we have the gradient of g is 0. Okay, and so writing this out, this is just phi squared gradient f plus 2 phi gradient phi times f. And I'm going to rewrite that as phi squared times gradient f. And then I'll get a, let's see, gradient I phi on phi cubed times g, okay, which looks a slightly strange way to write it. So, but the nice thing about writing it that way is that now when I compute the Laplacian, actually let me just make a comment there that I have, from up here, I have gradient f. That gradient f at this maximum point is just going to be equal to 2 gradient phi on phi times f, right? So we'll use that in a minute. Okay, so I want to compute, the other thing I know is at the maximum point, we have also that Laplace g is less than or equal to 0. It's the maximum point. And now if I compute that, I just want to differentiate through in this equation that I've got. And the way I've written it makes that very simple, because if I differentiate the phi squared at the front, then I get the derivative of that times the bracket, which is all 0. So that term I throw away. And also when I differentiate the g, I get 0, because gradient g is 0. So I only get 2 terms, phi squared, and I get Laplace f, and I get the gradient of this gradient phi on phi cubed. Okay, so I get, sorry, I'm missing a 2 there, aren't I? So I get 2 Laplace phi on phi cubed, and I get a minus 6 gradient phi squared on phi to the 4th times g. Now I'm going to write the g again as phi squared f. Okay, all right, so now I'm going to use the equation 2 that I derived up here to plug into there. So I get, this is going to be greater than or equal to phi squared, and Laplace f is greater than or equal to 2 over n f squared minus 2 root f gradient f. And there I'm going to plug in for gradient f this expression from here, which is 2 gradient phi over phi times f. Okay, and then I still have these other terms. So 2 Laplace phi over phi minus 6 gradient phi squared on phi squared f. Okay, now let me take out a factor f. So the first term will then become a 2 over ng, and the second term, okay, converting things to f's now. So the root f I want to write as so I'm going to take one of the phis times root f as a root g. Okay, so for root g, and then I'm left with a gradient f, gradient phi, sorry. And then the other terms I've just taken out the factor f, right? So I'm just going to get a 2 phi Laplace phi and minus 6 gradient phi squared. Okay, so let's see. Now I can write that as greater than or equal to, let's say, if I just use Cauchy-Schwarz on that second term there, I can still have a 1 over ng, say, at the expense of some constant times gradient phi squared. Okay, and then I still have this 2 phi Laplace phi. Okay, well, so now we need to check what phi looks like. Well, so phi is 1 minus rho squared. Gradient phi is minus 2 rho gradient rho, and so gradient phi is bounded by 4 rho squared, and rho is less than or equal to 1, so that's less than or equal to 4. So the gradient phi is bounded, and the let's see, Laplace phi is minus Laplace rho squared, so that's greater than or equal to minus 2n. Okay, so if I put those together, then I get exactly what we needed. So the 1 over ng, so the thing in the bracket has to be less than or equal to 0, and that says exactly that g is less than or equal to something that depends just on n. Okay. So that's it. That's the proof of the Yau gradient estimate. Yeah, so phi squared g being bounded is exactly the statement in the claim up there. Okay, any questions there? So it's really very elementary, but you just have to find the right function to apply this to. All right, so what do we do with this? One of the really nice consequences of the Yau gradient estimate is Harnack inequality. That's a very simple consequence. So this just says that if you have a positive harmonic function, let's say on the ball, then on, let's say, the half ball, you can, the values are comparable to each other. So particularly the soup on the ball of radius r over 2, about x naught of u, is bounded by some dimension-dependent constant times the int on the same set. Okay, so that follows very easily because let's see, on the ball of radius r over 2, we've got now a gradient bound on log u. Okay, so again, let me yeah, I can rescale. So let's rescale so that r is 1 again. So then on the ball of radius a half, about x naught, we'd have a uniform bound on the gradient log u. Okay, so it's just bounded by some constant depending on n. And integrating that up, I get that u of y over u of x is bounded by, what is it, e to the c of n times the distance from x to y inside that ball. And the distance from x to y in the ball of radius r over 2 is never bigger than r. In this case, it's 1. Okay, so that's all there is to it. So the ratio of values at any pair of points is bounded by e to the c. Okay, so that's well, it's precisely the classical statement of the Harnack inequality in a Euclidean case. All right, now there's one more ingredient that I need to get to the proof of this result on harmonic functions of polynomial growth, and that is a mean value inequality. Okay, so this, okay, so I think this is first due to Peter Lee and Rick Shane. So the theorem says that, okay, let's assume well, actually the same conditions that I assumed before. So it's the manifold is complete non-compact with non-negative Ricci curvature. Okay, so let me not write those down again. Yeah, okay, so what did I just do? All right. Okay, if V is a non-negative subharmonic function, again, let's say on a ball of radius r, about x naught, then V, let's say the central point, is bounded by some dimension-dependent constant times the average on the ball of V. Okay, so this mean value inequality. So remember, we started out looking in the Euclidean case at harmonic functions as things that satisfied this mean value equality. In the Euclidean case, you can get very quickly from that to the mean value inequality for subharmonic functions by using the mean value identity for averages on the boundary of the ball. But it's not so easy to do that in this manifold setting. In fact, I'm not going to prove the full result here. What I'll prove is just a very special case of that, which is the case where V is U squared and U is harmonic. Okay, so remember, so subharmonic just means that Laplace V is greater than or equal to 0. Right? Okay, so the only case that I'll need actually in the proof of the theorem is the case where v is just the square of a harmonic function, and of course if you have that, then Laplace v is just 2 gradient u squared. Okay, so it's certainly greater than or equal to 0. Yeah, so that doing that case actually will save an extra step, an extra page or two of computation. So I think it's worth doing it this way. So let me observe there's one case of this result which is very easy, and that is, so let me do that case first. If H is harmonic, then, okay, and let's say non-negative, then by the Harnack inequality that I just proved, you get the, well, okay, so H at x naught is certainly less than or equal to the sup on the ball of radius r/2 about x naught. Okay, and the Harnack says that's bounded by constant times the inf. Okay, but the inf is always less than or equal to the average. Okay, so that's less than or equal to C of n times the average on the ball of radius r/2. Oops. Of sorry. Okay, that's the inf of v, and this is the average of v. Sorry, h. Okay. Well, that's not quite what I want to say. I want to say it's less than the average on the whole ball, but I can write this as the integral on the ball of radius r/2 of h divided by the volume of the ball of radius r/2. And of course, since h is non-negative, that's less than or equal to the integral on the full ball divided by the measure. So now I want to multiply by br x naught divided by br/2 of x naught. Okay, and now I'm saved by the volume comparison result. The ratio of the volume of the ball of radius r to the volume of ball of radius r/2 is no bigger than 2 to the n. Right? So I get 2 to the n C of n, and this is the average on the ball of radius r. Okay, so in the harmonic case, it's a very direct consequence of the Harnack. You can think of this mean value inequality as being some kind of a weaker version of the Harnack that holds for subharmonic functions. Okay, so let's look at the case we're really interested in, which is where v is u squared and Laplace u equals 0. Okay, so I'm going to actually use case 1 to some extent. So I'm going to let h be the harmonic function. I'm going to cheat a little bit here, okay? So I'm going to assume solvability of a Dirichlet problem. So I'm going to let h be the harmonic function on, let's say, the ball of radius 1/2, I think. Yeah. With boundary value, so h on the boundary of the ball of radius 1/2 should agree with, well, let's say the absolute value of u. Okay, so we just, yeah, on the boundary of this half ball, I just take absolute value u, so that's a non-negative function, and then I'm claiming we can find a harmonic function which has boundary values equal to that non-negative function. And so on the interior, actually, it's going to be strictly positive as a result of the Harnack inequality. All right, so that means that, well, H, okay, what do I want to see here? So U squared is subharmonic. In fact, I guess what I want is that, yeah, absolute value of U is subharmonic. And so that implies that absolute value U at x naught is bounded by H at x naught. Okay, so let me write that as U squared at x naught is bounded by H squared at x naught. Yeah, and so let's see, so that was bounded by constant, let's see, I think this works out, let's see. So I get the average on the ball of radius r about x naught of H squared, and yeah, that should be less than or equal to the average of H squared. Yeah, just by Hilda. Okay, so all right, so that obviously doesn't do everything I want to do. I want to bound U squared at x naught by the average of U squared, okay? So now we have to work a little bit harder. So I want to write, in other words, I need to estimate this average of H squared by the average of U squared. Okay, so to do that, I'm going to write, okay, so let's just look at the integral rather than the average for the moment. So, so let's see what this R, sorry, we're doing this on the ball of radius a half, so this R here is a half. Okay, so integral on the ball of radius a half of H squared. So I'll write that as, so it's H minus absolute value U plus absolute value U. Okay, and then if I just expand that out, that's bounded by, let's say, twice integral of H minus absolute value U squared and twice integral U squared. Okay, again, on the same set. And the important thing to notice is that this function here is 0 on the boundary. Okay. The integral U squared is fine, that's what I want, right? I want to bound everything here by really integral U squared. So what's left is to try and bound this integral of H minus U all squared by integral U squared. But the fact that it's 0 on the boundary means I can apply the Poincare inequality. Okay, so I get integral H minus absolute value U squared is bounded by some constant times the integral of its gradient squared. Now, U is smooth, absolute value of U is still W12, right? So there's no problem with doing this. And now if I expand that out, this is bounded by, again, a constant times, well, I get one term, which is gradient H squared, and the other term, which is gradient U squared. All right, and okay, so now I'm going to use the fact that H is harmonic. And harmonic means that it minimizes the Dirichlet integral amongst all competitors with the same boundary data. Okay, and that says that the integral on the ball of radius a half of gradient h squared is less than or equal to, well, the Dirichlet energy for anything else with the same boundary data, and that means in this case absolute value u. Okay, so it's bounded by the gradient of absolute value u squared, but that's just the same as integral gradient u squared. Okay, so really both of those terms on the right-hand side, the gradient h squared and the gradient u squared, I can bound by gradient u squared. Okay, so remember what I'm trying to do. I'm trying to bound everything by an integral u squared. So in the last step, I need to try and show that the integral of gradient u squared can be bounded by the integral of u squared. All right, so let's see. I'm going to let, so far on the ball of radius a half, and I want to end up with an estimate on the ball of radius 1. So I'm going to let, say, phi be a, well, let's say smooth function on the ball of radius 1. And let's say that phi is identically 1 on the ball of radius a half, and so compactly supported in the ball of radius 1. And then I can certainly do this and make the gradient phi bounded, okay, by some constant that depends only on, well, it doesn't really depend on anything. Bounded by 2, I think, would be just about, or 2 plus epsilon perhaps. Okay, so then let's compute. I'm going to use, so here I'm using the one point where I use the fact that u is subharmonic, that u squared is subharmonic. Yeah, so if I compute integral on the ball of radius 1, phi squared gradient u squared. Okay, and I'm going to take one of the gradient u's and integrate by parts here. So I'll get, of course, no boundary term because phi is 0 on the boundary. I'll get a term which is phi squared u Laplace u, and the other term is what do I get? 2 phi u gradient phi dot gradient u. Okay, so u is harmonic, so that one's gone. And the last term I'm going to expand as, okay, I'll get a phi gradient u, so phi squared gradient u squared to the half times u squared gradient phi squared to the half. Okay, good. So the nice thing about that is the first bracket is just another copy of the one I started with. And so what that tells me is that the integral of phi squared gradient u squared is well, bounded by 4 times integral of u squared gradient phi squared, and gradient phi is bounded, so that's just some constant times integral b1 u squared. Okay, and on the left-hand side, because phi is equal to 1 on the ball of radius a half, this is greater than or equal to integral gradient u squared on the ball of radius a half. So that's really the inequality I want. The integral on the half ball of gradient u squared can be bounded by a constant times the integral on the full ball of u squared. All right, so if I put all those pieces together, I get that integral h squared, let's see, where were we? Here. I get a term which is integral on the half ball of u squared, and I can bound that by the integral on the full ball. And then the other term is now bounded by some constant times the integral on the full ball. Okay, so what we end up with is integral b a half h squared bounded by some constant times the integral on the ball of radius 1 of u squared. Okay, and that almost finishes what I want to do. So putting that together with the inequality up here gives me that u squared at x naught is bounded by some constant. That was an average on the half ball, so divided by the volume of the ball of radius a half times the integral of u squared on the ball of radius 1. And then in the same way as before, using the volume comparison theorem, that would be no bigger than 2 to the n c times the average of u squared on the ball of radius 1, which is what I wanted to prove, right? That's exactly the inequality that we wanted. Okay, so that's the mean value inequality. So as I said, I mean, Lee and Shane proved this for arbitrary subharmonic functions. The proof I gave you here, where it's just the square of a harmonic function, is a little bit easier, but you can do the general case. In fact, a lot of the proof is the same, but there's one more step that's needed, which still takes a page or so of computation. So I won't do that. Okay, so let's go back to the main theorem. Okay, looks like I'm not going to get through the whole proof, but at least I should get a fair bit of the way there. Okay, so the main result that I am aiming at is this result by Kolding and Inequality that says the dimension of the space of harmonic functions of polynomial growth is bounded by some purely dimension-dependent constant times p to the n minus 1. Okay, and where this HP, remember, was the space of harmonic functions which have polynomial growth of order p, which means that u of x is bounded by some constant times, let's say 1 plus distance from x to x naught to a power p. Okay, and yeah, so this is Kolding and Inequality. '96. And as I said, the proof that I'm following is actually much closer to the one that Peter Lee gave, also in the same year. Okay, so the proof uses two lemmas. So the first one, let me write it down. I'll try and explain a bit about what it says. So let's see. Let's suppose that we have any finite dimensional subspace. Okay, so we don't know a priori that this space is finite dimensional. So, but it's enough to bound the dimension of any finite dimensional subspace. So let's take K to be any finite dimensional space. Okay. In this case, I don't need the polynomial growth. So this is just a subspace of the space of harmonic functions. Okay. Then, well, that's a pretty wild space of functions in general. There's no canonical choice of inner product that you can put onto it, but I can put on it, for example, the L2 inner product on any suitable subset. And this lemma says if I choose a basis, okay, so I equals 1 to k, little k, so this is going to be any orthonormal basis for k, and orthonormal meaning with respect to the inner product L2 on the ball of radius r about x, okay, for some x. Okay, so that means, okay, well, right, what I mean. So the conclusion is that for any epsilon, let's say positive, but no bigger than a half, say, the integral on a slightly smaller ball, so let's write this as b r times 1 minus epsilon about x. Okay, so, and I'm going to take the sum I equals 1 to k ui squared is bounded by some dimension-dependent constant times epsilon to the minus n minus 1. Okay, so that's the statement of the lemma, and just let me make a few remarks here. So the content of this lemma is really the statement that, well, in a sense, you can't fit too many harmonic functions into a small space. So let me just make the observation here that the right-hand side doesn't depend on k, right? Independent of k. Now, on a complete manifold, the space of harmonic functions is, of course, infinite dimensional. So I could choose k to be a subspace of dimension as high as I like here. But the right-hand side is independent of k. And that's saying that no matter how many harmonic functions are in this, you know, how big the dimension of this space k is, if I look at the L2 norm of this basis restricted to a slightly smaller set, r times 1 minus epsilon, then that can't get above some threshold, which is independent of k. So you can keep on throwing more harmonic functions in, as many as you like, but they all have to be concentrated around that outer strip of width epsilon eventually, once you get to a large enough dimension. Okay, so that's kind of the content of this thing. So the right-hand side, I should say here. Yeah, so if I look at, seems to be able to write anymore.
Hey Ben, just a quick question.
Yeah.
Is this an L2, strictly L2 phenomenon, or can you do it in other Hilbert spaces?
When you say other Hilbert spaces, what do you mean by that?
Like a Sobolev space or something on the ball.
Other Banach spaces. You could get a statement like this for other Banach spaces, like LP spaces and things, but it's probably not so useful. So you don't have a concept of orthogonality for a start.
Yeah. I mean, like H1 or H2 or something.
Oh, I see. That would be a bit trickier. Yeah, I mean, this, as you'll see, this is really an application of the mean value inequality. So unless you have you need a mean value inequality which tells you about higher derivatives if you want something that controls sort of an H1 norm, for example.
Okay, thanks.
Yeah. Okay, so by definition, we have the integral on the ball of radius r about x of ui times uj is delta ij. So this is what I mean by being orthonormal with respect to L2 of BR. And so in particular, that would say that the integral on ball of radius r about x of the sum I equals 1 to k ui squared is just k, right? So on the whole ball, I have the integral is k, but this is saying that when I shrink down to the ball of radius 1 minus epsilon times r, then it's immediately dropped down to something that doesn't depend on k. Okay, so it's rather a beautiful statement of the fact, well, yeah, that kind of principle that you cannot fit too many harmonic functions into a small space, right? Okay, I think I can probably just about prove that. Well, let me, yeah, okay, so I'm going to actually prove the first part of this and maybe not the full statement just yet. Okay, so again, as always, things are scaling invariant, so I can assume that r is 1. And so then what I will do, first of all, I want to bound the integral on the ball of radius r times 1 minus epsilon of this thing. So first of all, I'm just going to bound the value of this sigma ui squared at some point, right? So let's just choose some point y, which is in the ball 1 minus epsilon. Okay. Well, okay, so the idea is we've got this k-dimensional space. I'm just going to choose, so I fixed y now. I'm going to choose a rotation of rk such that, okay, so let's call this a O, our rotation. So I want the rotation of the values of these basis functions at y. So this is just the vector u1 at y up to uk at y. I want to just rotate that so that it's, well, the length is the same, of course. So I get sigma I equals 1 to k ui squared at y, square root, times just 1, 0, 0, right? So I just rotate everything so that it's pointing in the E1 direction, if you like. Okay, and so this thing here is just the sum of the components of the matrix. So it's O1I, UI, Y, etc. Okay, so we can always do that, of course, just by Gram-Schmidt or something. And now I'm going to let U be the function. So this is sum over I, U1I, UI. Okay, so this is, again, a harmonic function. Okay, so then the mean value inequality that is proved, this allows me to bound U squared at the center point, sorry, this is at Y. Okay, I can bound that by some constant times the average over a suitable ball of U squared. Okay, and well, what's the ball? Let's draw a little picture here. So we've got, remember this ball of radius 1, about x, right? And sitting inside that, we've got a slightly smaller ball, radius 1 minus epsilon. Oops. This is b1 minus epsilon about x, and y is just some point inside here. So I want to choose a ball that fits inside the ball of radius 1. Okay. Now remember, this is actually in manifold, so this is kind of schematic here. So I'm going to choose this to be the ball of radius 1 minus rho of y about y. Okay, so that's this one here. Okay. So it's centered at y, but it's the biggest one I can guarantee is contained in the ball of radius 1 about x. Okay. So let's see. So that's constant. I get integral on this ball, u squared, divided by the volume of the ball. Maybe that's about y. And of course I can, because this ball of radius 1 minus y is contained in the ball of radius 1 about x, I can bound that by the integral on b1 of x, u squared. Okay, now I'd like to have the average on the ball of radius 1 here, so I have to multiply and divide by those volumes. So I get the volume of b1 of x divided by 1 minus b1 minus rho about y. Now the trouble is the volume comparison doesn't directly allow me to pair volumes about points with different centers. But I can observe that the ball of radius 1 about x is contained in a bigger ball about y, something like this. Right, so this would be the ball of radius 1 plus rho about y. So that, I didn't draw it very well, but that contains the ball of radius, just by a triangle inequality, that contains the ball of radius 1. So I get C, and now I get B1 plus rho about y divided by B1 minus rho about y. And now I have the same center, and that's times the average of u squared on the ball of radius 1. Okay, and now I can use the volume comparison to bound that by C, 1 plus rho on 1 minus rho to the n times average of u squared on the ball of radius 1. Now, we're almost done. Let me just remark at the end here, the integral on the ball of radius 1 of u squared is just 1. Because remember, I got u as a rotation of the ui's. So it has, it's a rotation of an orthonormal basis, and so it has length 1 in L2 of B1. Right? So we have this term here bounded. So there's an easy estimate now, which is not the optimal estimate. Oops. Okay, so the easy estimate is that on the ball of radius 1 minus epsilon about x, I have that 1 plus rho on 1 minus rho is less than or equal to, so rho is less than 1 minus epsilon, so this would be less than, say, 2 over epsilon. Okay, and so that would give me that u squared at y is bounded by some constant. I get a 2 to the n, which I'll just absorb into the constant, times epsilon to the minus n, and then I get 1 over the ball of radius 1 about x. And so integrating on b1 minus epsilon, I'll get sorry, here I need to use the fact that this is sum I equals 1 to k ui squared at y. Okay, so when I integrate, I get the thing that I want. Sum I equals 1 to k ui squared would be bounded by constant epsilon to the minus n, and now I get b1 minus epsilon divided by b1. Okay, and this part is just bounded by a constant. That's almost good enough, except that what I want is a power n minus 1 instead of a power n. What we'll see is, in fact, that translates to the same power in the main theorem, right? So that would be enough to prove an estimate of the form p to the n instead of p to the n minus 1. Okay, so I'm going to stop there. Next time I'll go through how we improve that exponent, and then we're actually pretty close to the full result. Okay, any questions at that point?
Oh, my I didn't know my sound was still on. Yeah, thanks, Ben. Great talk. I just had a quick question, or maybe you can just confirm that this is correct. The estimate, it sort of not only says that, so this lemma.
This lemma, yeah.
Yeah, it doesn't only say that.
I just got home.
Yeah. But I mean, yeah, let's let me ask this question. I love you. I'm glad you're home. It doesn't only say that, like, there's a limit on how many harmonic functions you can pack into a ball. Like, it's also saying that the growth rate of the harmonic functions as you expand the inner ball towards the boundary is proportional to the volume growth.
Well, I guess it says something like that. Yeah, I mean, the point is you can pack in there are as many functions as you like on the ball of radius 1, say. Think about the Euclidean case. But so it's saying that as you pack more in, they are necessarily concentrated near the outer boundary.
Yeah, and like as you thin.
No, you mean the epsilon? The epsilon dependence is, yeah.
Yeah, as you take the thinness, like as you make that strip thinner and thinner,
yeah.
The like extra functions that you get is like exactly this rate. It's exactly this growth rate.
This epsilon to the minus n minus 1, right? Yeah, that's right. And yeah, I mean, as we'll see, that's sharp by looking at the Euclidean case, right? If you work out what happened in the Euclidean case, then you can see that this is sharp.
Yeah, cool. All right. Yeah. I just wanted to make sure I understood that properly because it seems really amazing.
Yeah, no, it's a very nice little result.
And sorry to the people in the chat. Yeah, there was a daylight savings time change. We had it on Sundays.
Yeah, right.
Can I ask a question? So does this only hold for balls in non-compact manifolds, or can you make this argument just locally, or does it just depend on all that other stuff that it's
almost local? But I use the so I use the mean value inequality, which means I use the Poincare inequality, and my proof of the Poincare inequality assumed that it's non-compact. But all you really need is something like there are points of some positive distance from the ball in the manifold, and then you get some constant which depends on that distance, I guess. So as far as it goes here, yeah, you do need things to make sense outside this ball, or you need a Poincare inequality on the ball, and then everything works fine. Yeah, okay. So, right, so next time I'll finish off that proof. Really the point is here, in this last step, I was just estimating this function by its maximum on the ball, but in fact, of course it gets large near the boundary, but it's small everywhere else. So the integral, you should be able to estimate not by the maximum, but by something better, right? Using the fact that it's smaller when you get away from the boundary. So that's the argument I go through next time, which uses the Laplacian comparison theorem. And then we need, okay, so far I haven't used the polynomial growth at all. The second lemma is really exploiting the polynomial growth part of it. But I'll leave that till next time. Good, any other questions? No? Okay, so I think I probably will need maybe half an hour of next week, not the full time. Good, cool. Right. See you then.
Thanks, Ben.
Thank you, Ben.
Okay. Oh, by the way, so you don't have some fixed schedule for the future talks, right?
Not really, no. I was going to say we should get you to talk about the ancient mean curvature flow, ancient convex mean curvature flow result. That'd be nice.
Yeah, actually, if you're interested in some ancient flow for a higher order flow, like a Gauss curvature, maybe it would be good to give a chance to talk to my friend, Jun Choi.
Oh,
yeah. Yes, some
okay,
visual.
that would be great.
Yeah, later.
So we have Ben will speak next week, and then maybe Glenn will do 2 weeks, and then Julie 2 weeks. Is that right? Roughly?
Roughly, yeah.
Yeah.
And then, so that gives us whatever 5 more weeks, and so you have lots of time. You have 5 or 6 weeks to prepare something.
Okay.
Yeah, but that would be great. So, love that if you could do that.
Where is Byung-Jun now? Is it Canada?
He's at Toronto.
So we need to work out about a suitable time.
The
time zone might be difficult. Yeah.
No, he's okay. He sleeps at 3 or 4 p.m. I mean a.m.
Okay.
A.m. Yeah.
All right. Yeah.
I think by then we'll be into our out of our semester time, so we should be able to move this.
Yeah.
To a better time for him.
No, it's okay. He's a late sleeper and late weeker.
Sounds good. Yeah.
But yeah, we can easily adjust the time, and then we have recordings, so it's no problem.
Yeah.
So Ben, in the case where you're on some kind of maybe a warped product or something like this, can you kind of imagine your harmonic functions as getting really close to your eigenfunctions on the sphere? Is it kind of what's happening?
Right. So I guess in the warped product case, you do have these analogs of the spherical harmonics, which are product of an eigenfunction on the sphere with some function, some radial function, which depends on your geometry.
Yeah.
Yeah, that's right. So you always have a basis of that form.
Yeah.
And so I guess in that case, it's saying something about the warping function on those harmonic functions has to grow quickly if the eigenvalue is large. I think that's what it's saying in that situation.
Right. Yeah. Right. So it kind of sort of is really, really flat right up until the end.
Yeah, that's right. That's right. Yeah. I mean, in Euclidean space, these would be power functions, right? So when the eigenvalue is large, it would be radius to some large power, which is just like that. So it's
And is there anything stopping that kind of thing happening in negatively curved spaces, or does that? Is it just the picture completely different then? I mean, how much are we using positive curvature here?
The epsilon dependence would be different. You get a result like this, but the epsilon dependence would be very different.
Right.
Because, I mean, let's see. So in that case, you clearly get uncountable dimension for those spaces.
Right. No, I don't see that. Why would you get that?
Because well, even the bounded harmonic functions have uncountable dimension in the hyperbolic case, right? So in the hyperbolic situation, you have you can solve a Dirichlet problem in infinity.
Yeah.
So you have basically arbitrary boundary conditions on the sphere at infinity, and you can get a bounded harmonic function that way.
Yeah.
Yeah, so all of these polynomial growth spaces would include those, right? So,
Right.
yeah. I think the place where that falls down in this argument will be mostly in the lemma 2 that I talk about, which uses the volume growth